guessing that lots of people here have already gone off the MLP, which is why there's not too many people in the room. But for those of you who are still around, so just a quick introduction. So Stella did her undergraduate degree at Brown University and then did her PhD in Edinburgh and has stayed on to this postdoc. And she's basically been working on different kinds of models for trying to learning different aspects of language acquisition. She's got a talk at EMLP, Ongoing Learning of Morphology and Syntax, but today she's going to be talking about some more recent work on learning phonetics, semantics, and lexicon, all simultaneously.
Thank you. So at some point at the very beginning of your life, right after you were born, you started learning a language, maybe two languages at once, maybe even more. And I'm guessing at this point you've probably forgotten how that happened, what was involved. So today I'm going to be talking about the very first steps. What are the things that you have to learn before you even start producing language? So as a baby, you're confronted with this noise coming from the people that you care about, and you have to figure out what this noise means, what is it about, how is it structured. One of the first important things you have to figure out is what are the sounds in that noise. So no two sounds are exactly alike, but some sounds are more similar than others. Some sounds are meant to be the same sound. And you have to figure out this categorization of sounds into phonetics, which is what I'll be talking about today. A second important aspect is that the noise isn't a random variation of stuff that is always different. There are bits that repeat. We call them words. And as a child, you have to build up an inventory of these words, a lexicon, that you can then use to produce your first word, and then you get your parents all excited. And obviously this noise is about something. It's situated in the world. It's about what's going on around you. It's about what you're doing. So there's this link between the language and the real world that you have to learn. And an important aspect here is that all of these processes don't happen at once. They happen over a long span of time, and they happen at the same time. So for the first year, 2 years of your life. And so if you're trying to model the process of language acquisition or the task of language acquisition, you could do each task at once, or you could build a joint model that tries to capture the interactions between these different subtasks that you have to learn. And this is what I'm going to be talking about today. So joint models are useful because they capture this realism of the interaction between tasks, and often we find that they perform better because you can leverage the information from one task to help with learning another one. So specifically, today I'm going to be talking about learning phonetic categories. We're going to look at a single task model and show that it, in fact, doesn't work. But then if you add some constraints in the form of also learning a lexicon at the same time, this is Naomi Feldman's model, your performance on this task of learning phonetic category improves a lot. And then I'll be talking about the current work I'm doing, which is extending this model with a form of semantics in the form of a topic model. So unlike a lot of other things that we do in linguistics, computational linguistics, phonetic categorization begins with a continuous input. So when we do parsing or pulse tagging, we're faced with discrete input. Here we have continuous input, and we have to figure out where the categories are, where the boundaries between the categories are in particular. And all of the stuff is continuous, but humans don't notice that. They have categorical perception. They think that if you vary a sound, if you vary the voice onset time, for example, between t and da, they will tell you that they're hearing two different sounds when really they're just hearing a continuum between those two sounds. So how do you learn that boundary? So there's this interesting experiment by Maya et al. In 2002 showing that you can teach infants that boundary by giving them statistical input. So basically, by varying the statistical distribution of their input, they will draw that boundary differently. In particular, if you, again, looking at the voice onset time data, the ta-da continuum, if you give them a uniform distribution where most of the input is coming from the middle and you test them on the extremes, they won't hear a difference between those two sounds. But if you give them input that's coming from two different distributions near the ends of the continuum, they will learn that there's a difference between these two. So infants are sensitive to the statistical regularities of sounds in the input. And so we can leverage this in the models that we use and assume that and use the statistics of the input to learn these categories, just as infants did in the study. We're not looking at voice onset time here today. We're looking at vowel categorization, which we represent using the formants, the first two formants. These are spectral peaks in an acoustic signal. I'm not going to go into any more detail than that about what they are. But essentially, we're representing our input data is two-dimensional and continuous. And there's been some other models using formants, trying to categorize vowels using formants, making this assumption that formants come from a Gaussian distribution. One thing to note here is that they're actually, all of these models have been tested on a small number of vowels that are quite far apart, and we'll see why that works and why a more general model doesn't work later on. So as I said, we have continuous data. If we're making this Gaussian assumption, we assume that we can find a set of Gaussians that are responsible for producing the data points that we see. And then we can categorize the data points based on which Gaussian is responsible for generating that data point. So this is all well and good if your Gaussians are well separated. Unfortunately, when you look at the English vowel space, it looks like this. It's a mess. All of the different categories are overlapping. So this is data from Hillenbrand from 1994, where they got English speakers to produce vowels in the context of words and then manually found the formants for these vowels. And so they're categorized by they're labeled with the correct vowel sound, so the sound that the speakers were intending to produce, and yet they're really right on top of each other. The two different categories sound really similar.
So if I'm wondering if there's if it's because you didn't include some features or if they really sound the same. So do these sound vowels that were produced from, they're supposed to be different, but if you played them to a human, could they tell?
They can tell the difference to some fairly high accuracy, yeah.
Even if they...
So it is a overly low representation that we're working here with if we're just using the formants. So that is part of the problem, but it's not quite clear what the rest of the representation should be, I guess. So the data that we're working with is generated using the categories found by Hillenbrand et al. So we create Gaussians based on the empirical data points and then generate data from that. We flip the axes too, that's why it doesn't look like the previous graph. And if you fit a Gaussian mixture model to this, as predicted, it really doesn't do well. So the orange, the gold clusters are underneath, and the blue clusters that the model finds are on top. And you see that there's relatively few clusters, and they just cover the space as well as they can, but they don't find that internal categorization where you have the overlapping categories. And clearly, the problem is that there's no context for these individual vowels. So if you have 2 points that are really close to each other in the space, you have no knowledge about whether there should be one drawn from the same category or 2 overlapping categories. However, this is the insight from Naomi's model, that if you know that these vowels are being produced in the same word, it's really likely that they're actually coming from the same vowel category. Whereas if they're being produced in the context of 2 different words, then maybe they should be in 2 different categories. So basically, this joint model of learning the words and the vowels gives you this kind of constructive constraints, where if you know the identity of the word that the vowel is being produced in, you know the vowel category. And if you know the category and the other phonemes, then you know the word identity. And then in a joint model, you just learn both of these at the same time, and you solve this problem jointly. So again, previously in the simple Gaussian mixture model, we just had points without any kind of context. We add the word context in the form of known consonant values. And this gives you at least 2 different words, but maybe there are more, depending on what the vowel identities are. And so, for instance, you could posit that there were 3 different words in the lexicon produced from 2 different vowels. So to reiterate, we're learning a lexicon as well as the vowel categories. We know the token word boundaries, so we assume the word boundary problem is solved, and we assume we know the consonants, but we have to learn the vowels. We also don't know the number of vowel categories or lexical items in our lexicon, obviously. We don't want to bound that.
I know this is a detailed question, but from the Hillenbrand vowel targets, are you getting F2 just from F2, or is it an F2 prime?
It's just F2 or it's what the data set gives us. I'm not an expert in this.
Vowels are represented by the exact value of F2, disregarding F3 or...
Yes, yeah. So we don't want to posit a fixed number of vowel categories or lexical items, and so we use these non-parametric processes in the context of our larger Bayesian generative model. In particular, we're using an infinite Gaussian mixture model, which will give us as many Gaussian vowel categories as the data will support, and we're using a Dirichlet process in the lexicon. And yeah. So this is a schematic of the generative process of this model, where you begin by generating the Gaussian vowel categories. You use those vowel categories in the lexicon. So you generate a set of lexemes. And then when it comes to generating a token, you draw a token from the lexicon, and you then, wherever there's a vowel category, you replace that vowel category with a draw from the appropriate Gaussian in the infinite Gaussian mixture model. And then once you've defined a generative process, you can then do inference using Gibbs sampling or variational Bayes. We use Gibbs sampling for this. So as a reminder, this is the results we got from the infinite Gaussian mixture model, where we found that it didn't find enough categories and it didn't capture these overlaps between the categories. Whereas the lexical distributional model here, where we're doing joint learning of the lexicon and the vowel space, looks a lot better. Like the boundaries are very close to what the gold boundaries should be. So obviously, I'll get to it in a second. Thanks. So in general, apart from the really large Gaussians, the other categories are doing really well, or really close to what the true vowel categories should be. But yes, we are getting this supervowel. We're getting what I'm going to call supervowels that cover the entire space. And the reason why we're getting these is because we have, because the data includes minimal pairs. So words that have the same consonant frame but should have different vowels inside the consonant frame. And the model is trying to collapse those into a single lexeme. So it has only one lexical item with a single vowel in there. And that vowel is the supervowel that's covering the space. So it can cover tokens of boat and beat and bet and bite by putting them into this one lexeme that's just B supervowel T. So this is one problem that we're trying to address in the extension that I'm going to talk about later. Another problem is that this assumption that we know the gold value for the consonants is pretty unrealistic, because we know that, if anything, children settle on vowel phonemes a bit earlier than consonant phonemes. And if we have noisier consonants, then we also have more potential minimal pairs, and so the supervowel problem might get worse. So despite this really productive interaction between learning a lexicon and the vowel categories, it's still not quite a solved problem. And in the rest of the talk, I'm going to be talking about what I'm working on now, which is trying to add semantics to this model and trying to see if that helps solve this problem. Why do we think it would solve this problem? If you look at some of the examples of the words that get conflated, it's clear to us that they shouldn't be conflated. They're different words because they have different meanings. They refer to different things. And what we're trying to leverage is that these words also appear in different contexts. So the child will encounter these words in different situations. So beats, for example, will happen at dinner time. Boats will happen when they're at the park near the water. Bats might show up at Halloween or in a book or something like that. So words with different meanings appear in different contexts. However, the child is still building up a lexicon. It doesn't know what these different words are. We're not trying to solve the word meaning matching problem. Instead, we just want to assume that the child knows what's going on in the general environment. And so what we'd really like to have is some kind of information about where the data that we get is coming from. So what we have is child-directed speech transcripts, but those usually don't have annotated information about whether this is now happening in the kitchen or in the park or etc. So that's what we'd like to have. We'd like to have like information about the actual physical context. We don't have that. However, if you look at the child-directed speech, most of the time it is about the actual physical context. It is about what's going on, what the child is doing. So you get these context-dependent utterances, like at dinner, they're going to talk about you like your beads, and look at the doggy when you're at the park, and so on. So the idea here is that we can use a topic model, which I'll get into in a second, to learn the topics for each context from what the mother or the caretaker is saying. So it's essentially a dimensionality reduction problem, in a sense, where you get all this input about what the words that the mother is saying, and then you learn a topic that covers that vocabulary. So if you know what an LDA is, or a topic model, you know that you learn, you get a set of documents. For each document, or what we're making the equivalence of a document is a context, so a situation that the child finds itself in. For each of these, you find a set of topics that covers that context or document. And you also learn a vocabulary for each topic. So you learn that the context is a mixture of different vocabularies, in a sense. What we want to use just the topics for each context. We don't want to use the vocabulary, exactly for this reason that we're not trying to learn a match between the child-directed speech and the topics because the child doesn't have access to those gold words. The child-directed speech is just a proxy for the environmental cues. So in a way, you could take the child-directed speech, replace all of those words by variables that match those words, and then do the same process as I'm doing here, but I'm not doing that because it's easier to look at real English words. So if you take the content words from the child-directed speech, you get input documents that look kind of like this. And what we're trying to learn is that when you have this in the child-directed speech or in the environment, you get topics that correspond to dinner time and kitchen and food. And this is what the LDA model will give us. Once we have those topics, we need to incorporate that into the lexicon. And we do that using a hierarchical Dirichlet process, which splits up the original global lexicon into topic-specific lexicons. And it's important here to note that these are the words that the child is actually learning. These are not the words from the lexicon, from the child-directed speech. So what we'd like is that the global lexicon splits up into topic lexicons where the vocabulary, you can have repetition between the words, but these vocabularies correspond to the different topics. So this is, for example, an animal type vocabulary, and this is the vocabulary for foods at dinner, and so on. Mm-hmm. Yes. Yeah.
Are you assuming already that you have those standard word packages?
Yes. Yeah. So the model is not doing the word segmentation problem.
So then you have those standard word boundaries, and you're trying to assign every word
That happens separately. I'll talk a bit more about that in a second, and then if you still have any questions, we can. So I'm now going to go through the full model, and hopefully that will explain what's going on, and if not, then please do ask again. So this is the generative process for the full model, the topic lexical distributional model, which is a bit of a mouthful. You start off, as previously, with the Gaussian mixture models that gives you the vowel categories. You use those in the global lexicon. You generate topic-specific lexicons. And on the side, we do this topic learning. So this isn't actually part of the generative process of this other model. This is just the input. We assume this as input to the rest of the model. We assume that we know the document topic distributions. And this is analogous to the child knowing what is going on in the environment, being able to observe the dinner time situation, the park situation, and so on. So then when it comes to generating tokens, these tokens now appear in the context of documents or situations. And when you draw a token, what I haven't shown here is you first draw a topic for that token from the document topic distribution. Conditioned on that topic, you draw a word from that topic's lexicon. And then once you have that word, that lexical item, the vowel generation happens as before. Mm-hmm. No. So the topic, the number of topics is fixed. It's parametric. We have 50 topics in the thing, so it's not. So it's a fairly small number. Sorry.
How does the lexicon get generated?
I'm using a Dirichlet process, a hierarchical Dirichlet process here. So you have a base distribution that's responsible for generating the lexicon itself, and then the. So it's a.
For all pairs of consonants, you can just put in any vowel sound.
Oh, the base distribution. You generate the length and then the consonants and then the vowels. So each bit of the word gets generated independently. So.
You started off by saying that you end up learning these super vowels.
Mm-hmm.
So I would sort of extend your terminology and say that results in these super words.
Yes. Okay.
So
I like that.
the
Yeah.
bat, bit, and beat, whatever, both bat and beat are all the same word. And you're saying that, look, this basically means that there is this highly polysemous word now. But we know words aren't that super polysemous. And therefore, if we give it some context, the lexicon will learn that these should be different words, right?
Yeah.
And so you're giving it some fairly wide context to decide what the semantics of the word might be. I would suspect that there's a lot of information in just collocation, so sugar beet versus sailboat versus cricket bat. Right?
Yeah.
The word to the left tells you that this word. So if you thought of sort of a model that also takes collocations into account, and wants to have low entropy on the collocation, you might get to the same thing. I don't know if it's in the model or not, because I came in a little late, so I don't know.
No, it's not in the model. You're looking at bag of words inside of topics. Yeah.
You might get even more mileage out of collocations, because collocations often have a much stronger cue than topic, which tends to be very diffuse.
It's a good point. I would suspect, though, that.
Much more predictable than the word next to it.
Yeah. On the other hand, this is child-directed speech, so you don't get things like sugar beet and cricket bat. You get the bat. There's not that many adjectives, and it's.
There are red boats, but there are no red bats, and there are no.
Yeah. Okay. I mean, it'd be something to. Yeah. 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 No. Yeah. Yeah. I guess this would be more. This model is a bit more robust to maybe missegmentation and things like that, possibly. Yeah, we do assume segmentation. If we didn't want to assume segmentation, then it. I'm going to think about it. Yeah. So in our experiments, we use transcript data from Childus, which is this collection of corpora of child-directed speech. We use the Brent corpus, a single child input from that. And as before, we convert all the words to phonemic form using the CMU pronouncing dictionary. And wherever we have a vowel phone, we generate a vowel from the Hillenbrand data as before. And we use Mallet, which is this LDA toolkit, to learn topics using the entire Brent corpus. So we learn topics based on a much larger data set. So they should be fairly robust to across children and across situations. We learn 50 topics, and we just use the content words for that. And the experiments that I present, the first set of experiments just use...
So are you resynthesizing or recording, and how are you creating this image?
The vowels.
You insert the vowel?
Yeah, just in the data. I mean, in the sense of we have a token that is a sequence of phonemes from the. I mean, none of this is auditory or acoustic. It's just we have single categories for the consonants, and then for wherever there's a vowel, we have this two-dimensional formant values that we generate from the Hillenbrand data. Does that answer your question? Yes. Yeah. No. Yeah. Yeah, so we first look at just the content words, and then the second set of experiments we look at using both content and function words. So there's some really early developmental, there's some developmental evidence from really early on in an infant's life that they make the difference between content and function words, like definitely within the first year when we're looking at this. So and content and function words are also pronounced very differently. So there's some evidence that we might, that children might just be attending to content words in this case. But we'd also like to see how robust we are to using content and function words in this corpus. So in terms of the topics that we get from the child-directed speech, these are some examples where each line are the most frequent words from one of the topics. So you get this, for example, a food topic, or a getting dressed topic, or cleaning up topic, and so on. We also get one topic that's the most frequent one, actually, that covers all the sort of light semantics, verbs without very much meaning that appear in lots of different contexts. And as I said a while ago, we wanted to look also at what happens if we don't assume as much information in the consonants. So what we did is we degraded the consonant set by collapsing some consonants together. So we erased the distinction between voiced and unvoiced consonants, and we just have one phoneme category that covers T and D and P and B and so on. That's the 15 consonant set. And the 6 consonant set just puts all of the stops into one category, all of the fricatives into another category. And so we're going to test the model on each of these consonant sets and see how badly, how much the performance degrades as we have less information from the consonants. We evaluate the tokens, both the vowel tokens and the word tokens, against the gold vowels and the gold lexemes and lexical assignments, using F measure, which is a measure for unsupervised cluster evaluation, which is made up of a thing that's similar to precision and a thing that's similar to recall. So you can tease apart the behavior of the model. Precision is called homogeny and recall is called completeness, just to make things interesting. So I'm going to talk about first, as I said, the data set that just includes the content words. I'm going to talk about the vowel results and then the token lexeme results. And we're evaluating the baseline lexical distributional model in blue against the topic lexical distributional model in red. And on the x-axis, you have the different consonant categories. So you see, obviously, as we have less information in the consonants, the performance drops quite a bit in terms of vowel categorization. You can also see that our model, which does better across the board, recovers better from having less consonant information, so that semantic information is helping something, is helping the model be more robust to noisier input. Unfortunately, when we look at the vowel categories themselves, we still get the super vowel. We have fewer tokens, vowel tokens assigned to the super category, but it's still there. So we haven't managed to eradicate it yet. In terms of lexeme results, the difference between the two models isn't as big, which is maybe surprising since we're putting more information into the lexicon rather than into the vowel categories. But this sort of shows nicely the power of joint learning, where you get improvements across the board sometimes. And again, our model, the difference here when you have fewer consonants is bigger than when you have more consonant information. So we're basically coming up with a more robust model here.
Can you help me reconcile those two? So if you go back to the vowel results, so let's say when you have all consonants, I mean, 15 consonants, getting a, I don't know, 3-4% improvement in whatever that VM is for the 15 consonants, so you're doing that much better on vowel categorization, right? So you have, but then if you go to the next slide, so there's a much smaller difference in the lexicon you learn. So what happened to the categories that you distinguished, and is it just a measure that VM is not showing that?
I think it's, to some extent, it's a measure because you have token problems. Like, it's a token-based measure, and the model has a lot of type information, so all words of a thing can be, many words that can be assigned to the same lexicon, the lexical item. So if you change that, you're changing a lot at the same time. You're changing the score quite a bit because you're measuring all of the tokens that have shifted if you've changed that one lexeme or that one vowel category.
No, I'm still thinking in terms of the minimal pairs that you have.
Yeah.
The hope is that the previous slide vowel results tell you that you've done a better job of breaking them up.
Yeah, so what's happening there is that words that aren't minimal pairs that might have been assigned to the supervowel before aren't being assigned to the supervowel as well. So those aren't going to improve the lexeme results because the lexeme category was correct. All of the words were assigned to the correct lexeme, but the vowel was wrong compared to the other vowel categories. Yeah. Yeah, the differences are really small.
Am I just seeing that?
Yeah.
Yeah, I mean, there's not a lot of room to go with that.
Yeah, so the categorization is quite good here.
I see, okay, so maybe I'm just being fooled by the picture. I
Yeah.
don't fully understand what the VM is doing.
It's basically measuring the cross-entropy between the two clusters, between the gold cluster and the whatever the model cluster is, in two different directions. So if you look at the subcomponents of VM, homogeny measures how clean the model clusters are. So what is the cross-entropy of the gold clusters within the model clusters? And here you see we have a better improvement. So we're merging fewer gold lexemes into a single model lexeme. So we are doing what we hope to do with adding the semantic information. We're separating some of the minimal pairs. And our recall measure, the completeness measures at the top stay about the same. So far the model's worked quite well. We've found better vowel and better lexemes. If we add function words to the content words, we still get better vowel results. These results are essentially the same as the previous ones. We still get the super vowel categories. The fact that we have one or two is just sort of a difference between different runs of the model rather than a qualitative difference between these two data sets. However, our lexeme results go way down because the function words are separated into topics when they really should be in the same topic. So that's what we're working on now, trying to figure out how to add function words to the lexicon in a way that makes sense for them being function words. And again, if you look at the components of the V measure, we get an increase in precision. So we're still creating better lexemes where we create them, but our recall has gone way down because the function words are being split up into different topics and then are split up into different lexemes as well. So in conclusion, I've gone through the sequence of models to learn phonetic categories, to learn vowel categories. I've shown that joint modeling is helpful. So this task really requires further information in terms of using either the word context, the word that the vowel appears in, and also the document context, the wider context of where the word is appearing. And this method of trying to recreate the wider context, the getting real-world information from the child-directed speech using topic models is new, and I think it's pretty neat. We're still working on how to incorporate function words into the lexicon and trying to figure out whether this is actually a crucial thing to do or whether we can just make this assumption that children separate function and content words into different spheres. And also we'd like to look at how well this model extends to other languages, whether this minimal pair problem is very English specific or whether you find it in languages across the board. And if so, does this model help there too? Thank you, and if you have any questions, I'd be happy to take them. Thanks. I'm going to sweep around across the room, I guess.
What are the words that are being assigned to the super vowels after you've added the topic?
They look pretty much the same.
So they're minimal pair.
They're still minimal pairs. Those are the only ones who can get collapsed, obviously.
Right. Yeah. So you have before you had minimal pairs, and then you were also assigning those super vowels to a bunch of other words that weren't minimal pairs, and you removed the non-minimal pair words.
For the most part.
Okay.
So, can you clarify this? The problem with the function words is it that there was a separate class, so that function words didn't show up in all the topics, but instead there was a separate topic for function words?
I think that might be the way to solve the problem, actually. Right now what's happening is because each situation only has probability in a few topics, so it has zero probability for most topics. There's no space for them all. And the words that appear in that situation have to be generated from that topic. So function words will appear in basically every topic across the board, but have to be assigned to one of the ones that has probability in that context. And if you have multiple contexts, they'll be assigned to different topics all over the place. And so then they get split up into different contexts. Sorry.
So, I mean, the function words are typically, auditorily, they're going to be more reduced, right? So they sort of have this flag on them.
Yeah, so that's sort of the argument. Like maybe children only really attend to content words when they're trying to solve this.
Are the vowel representations, the two-dimensional representations in the function word vowels,
they're the same vowels. They're not.
Okay, you don't have those reduced.
Yeah.
Okay.
So does anybody look at, say, a Hillenbrand, which is a replication of Peterson and Barney, what would that distribution look like for child-directed speech?
So I'm actually waiting on a data set of child-directed speech vowel formats.
Wouldn't you expect it to be much, much narrower distribution?
It's not as much as you think.
Well, because the child experiences speech from a handful of people.
Yeah.
But
Hillenbrand isn't that large either. So Hillenbrand doesn't have that many speakers either. So.
No,
but they're very diverse. Yeah.
Both sexes and
ages.
loosely controlled.
So I'm hoping to get this data set of infant directed speech vowel formats, which also is only a couple of letters. And it'd be really interesting to see how well that does.
Because you remember the last program was a study probably 50 years ago in which he said that he synthesized, please say what this word is, bit, and the bit sound was anywhere from bit to that. Then changed the performance in the precursor sentence and shifted the perception of the word through 3 different words. Which shows that absolute values of performance can be, the expected values of performance for particular vowels, especially the front vowels, can be moved around. Right? So it's less depressing to see the overlap among the ovals in that, when you know that there's this adjustment going on.
So that argues for adding acoustic context to the model as well as everything else.
Well, it says that in the context of a real speaker and a real listener, the space may actually be, the space within which the learning is going on might actually be much more constrained. Right?
Yeah, so maybe one thing to do would be vowels generated just from a single or a handful of people in the Hillenbrand data set. I know Naomi did one where she did some experiments where she only used male speakers, and she got a small improvement in her performance for just the lexical distributional model without the semantics. So there was an improvement, but it wasn't drastic.
There's also the fact that in child-directed speech, we charitably over-articulate and have prosodic frames that are very, very restricted, which help you to focus on the setting features.
I apologize, I was late to see my mention of script. Have you heard, I think Jeff Roy has the speech zone corpus?
Yeah.
Okay. What made me think of that was he had recorded the rooms of his house, right? So you can condition topic based on the room. Right? And just like, now that's the only extra salient information.
Do you know the release dates of that corpus, or like what come out? Because so far it's not.
I heard him talk about it at the 2009 inner speech.
Yeah, I mean, I've heard him talk about it.
I mean, I'm looking at his website. He says it's available.
Oh, okay.
Yeah. Not for public release, but your website says content. Right?
Okay.
Yeah, last I heard it wasn't available at all. So
Okay.
Yeah, I think he's waiting for the chat.
I wasn't aware that he was waiting for the kid to be some consent. That would take a long time.
Okay. Yeah. I'm curious. Okay.
Yeah.
So
But yeah, no, I mean that would be absolutely full data.
Okay. So you haven't tried to contact him?
No, but I will. Not that optimistic.
So sort of along those lines, if you started shrinking the number of topics times something very, very small, do your results stay the same?
Well, eventually it'll be the same model as the previous one. If you only have one topic, then it's
Yeah, no, I would say over like 5 instead of 3.
No, I mean, I don't think so. It's not a parameter that I've tweaked in a lot of people, but as you have fewer topics, they become easier and less informative. And so I suspect it becomes almost the time.
The other phenomenon I was thinking about in the context of this topic model is that if you are still getting these super words, it means that the real topics would not support it showing up in multiple documents. But there is some false topic you have learned which supports their occurrence in multiple documents.
Yeah,
so I was wondering if you can do some post-hoc diagnosis to see if it's true that for the superwords that you learn, that they're supported by some topic which doesn't match the true topics of those 2 or 3 clusters, the true clusters, like they should be different, but this one pseudo topic has crept in which appears to be in all of them and supports these words. If you have some evidence like that, you might be able to go back and change the way you do your LDA and require that topics be sparse across documents, meaning you aren't allowed to show up in too many documents. So right now the LDA criteria just look at a global thing. They don't care how often you use a topic. So the measure is more global, and this would be more per topic. You sort of require that there be distinctions.
So you do have sparse prior over the documents for each, over the topics in each document. But I guess, yeah, you're talking the reverse.
I'm saying sparse prior over the topics over the corpus.
Yeah.
So in the whole corpus, you're allowed to claim only a small number of documents. It's like the IDF measure, if you will.
Right.
Like, you want words to have high IDF.
So one thing that happens that's a bit frustrating is that if you fix the topics that you infer in this model to the same topic as for each token, it's the same topic assignments you get from the LDA model, the probability of the model goes down, but the performance goes up slightly. I'm still trying to figure out why that happens. So if you use the LDA topic assignment rather than the primary one, it separates those words better. Which is, I think, similar to what you're saying.
Because there isn't a common topic, there isn't a topic that would support the occurrence of boat, beat, and bat.
But you can have lexemes appear, the same lexeme can appear in multiple topics. So the
Yeah, no,
vocabulary
what I'm saying is that these minimal pairs may not be that kind.
Yeah, okay, yeah.
And therefore, to
look at
assume
the
that they
actual
exist,
topic.
you'll have to assume that there is some topic
Mhm.
for which there is a superword called whatever, boiad,